Cthulhu foughten, my friends. My name is Alhazred, and as ever, I'm here to teach you the eldritch magic of hacking. And I'm coming at you today with the first in a brand new series of YouTube videos where I'll be teaching you the strange, maddening art of writing your own custom malware. These will likely not be complete programs that we write in these videos, but more just individual functions, snippets of code that are meant to serve as a jumping off point for your own work and also to teach you how malware exactly performs the shrieking, immemorial lunacy of which it is capable. As always, the code and instruction provided in these videos is for legal penetration testing purposes only. These are the dark magics, but we should use them for good. Today, in particular, I'd like to do an introduction to the Win32 API, something that many programmers and hackers find a little intimidating at first. I'm going to show you why you shouldn't be so hesitant to start playing with it by demonstrating some process injection techniques. Relatively simple. It's really impossible for me to cover all of them in a single video right now, so I'll be tackling two of the simplest and most common right here, and there will be future videos to discuss more advanced, eldritch, complex varieties. Now, we're going to be doing a lot of this in Nim. Nim is a very obscure programming language, but if you've been on my stream, you've likely heard a little bit about it. It affords a lot of advantages to the would-be attacker. It is statically typed and compiled, but it has a syntax similar to Python. Before compilation, it's actually converted into C, which is in a different programming language, a low-level programming language. This gives us access to all of those low-level functions and low-level power, the memory manipulation that C has, as well as producing really small, compact, efficient, high-performance binaries. It's also a relatively easy language to learn, and it's a good way to show off how the Windows API works because it's relatively easy to read as well. So, nice readable code for this YouTube video. Of course, the downside is that this does violate the age-old credo of the Nim creator, who behooves us to, whatever we do, please not write malware in Nim. But you know what? You can't make a language that's perfect for malware without seeing some people use it to write malware. So I won't tell if you don't. Okay, cultists? Mum's the word, as the Britbongers say. Okay? Although, we're going to be using Nim for this demonstration, it's worth noting that to some extent, Win32 is Win32. Okay? The techniques I'm going to show you are going to be possible on really any language that can call the Windows API. The function calls will be identical, and the only difference would be language-specific data types, primitives, prototypes, declarations, and so on and so forth. With that being said, I just want to jump right into it. Rilya calls us. First, we need a very quick, very dirty explanation of the Windows API, specifically what it is and what it is used for. API stands for Application Programming Interface, and the purpose of such an interface is to essentially act as an intermediary between two pieces of software, allowing them to talk to one another. The Windows API, also known as Win32, is meant to provide programmers of Windows applications with an easy interface to access the lower-level functions of the kernel. As you can see in this image here, you should think of the Windows operating system as being arranged in layers, with the applications that users use, such as Paint, Notepad, and so on and so forth, all up here at the top layer, and the drivers and kernel down here at the bottom layers. These two layers do not speak the same language, and this is where the API comes in. The user applications don't talk directly to the kernel. Instead, well, in general, they don't talk directly to the kernel. In general, they talk to the Win32 API, the functions of which are located in dynamic linked libraries, or DLLs, such as kernel32.dll, GDI32.dll, user32.dll, and so on and so forth. These functions are actually abstractions of lower-level kernel functions, which are accessed through syscalls, and are easier to interact with while not changing much between Windows versions, while the kernel itself changes underneath of them. This makes it easier for applications to run on multiple versions of Windows, although the syscalls, which are the language that the kernel understands, might be different. Thus, the Windows API allows applications to easily communicate with the kernel without needing to speak the weird, primal, otherworldly language to which the kernel is accustomed. So here's a quick example of a syscall. Please don't be scared off by this. You don't need to know the details of this slide for the purposes of our demonstration today. I'm only showing it to you to illustrate the difference between the Win32 API and a syscall by showing you a syscall first. This particular syscall is nt-create-thread, which is actually being accessed on the back end by the Win32 create-thread function that I'll be demonstrating in a moment when we get into the... If you're curious, it basically works by moving all the appropriate function parameters into the appropriate CPU registers, and then you move the syscall ID, which in this case is 4EH, into the RAX register before you execute the syscall. Now, you see it being moved into the EAX register here, but if you remember your x86-64 architecture, you'll remember that the EAX register is just the 32-bit lower half of the 64-bit RAX register. So as you can imagine, executing syscalls is tricky and error-prone, and these tend to change a lot between different Windows versions, which is why create-thread exists to make this easier. So this is another quick, simplified look at how Windows manages processes. Each process is allocated its own private virtual memory space, and within that memory space, they'll all have various threads that are all operating independently with their own stack and their own registers, and so on and so forth. All process threads are managed by the thread scheduler, which passes the instructions to the processor at the appropriate time, making sure that all processes get the amount of CPU that they need. For our purposes, just be aware that each process has its own private memory space, and executing arbitrary code within a process or in another process requires the appropriate memory to be allocated with the appropriate permissions. Then your executable code needs to be copied into that memory space, and then a new thread is started to execute the code you just wrote in there. Again, you're going to see all of this right in front of your eyes in just a few moments, so it's okay if you don't really get it just now. This is a visualization of the use of the Win32 API function CreateRemoteThread. We'll see, again, we're going to see a code example of this very process shortly. But essentially, our executable running in userland is going to call the CreateRemoteThread function, which is located in kernel32.dll, and if you're writing in C, it's in the processthreads API.h header. That function will essentially be calling an unexported function in ntdll.dll called ntCreateThreadX. That will actually handle all the lower level registers and everything that the kernel syscall expects for us. This process makes our code easier to write, more compatible with more versions of Windows, and more resistant to errors. However, there are some drawbacks, particularly for us as attackers. Antivirus and EDR products can easily hook into these Win32 functions to detect them when they're being called and analyze their use. However, for a beginner's introduction to Win32 and process injection, this will suit just fine for now. Okay, so here we are in Visual Studio, and right off the bat, I'm going to urge you to resist the temptation to let your eyes glaze over and your brain slide off of what you're seeing. There's a lot of things happening on the screen right now, and I understand that. And we're going to tackle this line by line, and I promise you, that by the end of this video, you're going to understand, at least at a high level, everything this code is doing. Right off the bat, I want to point to over here on the right-hand side, you're seeing some text in green. This is not executable code. This is all just comments. I've gone through and painstakingly commented every part of this program that is interesting and involves the Windows API to illustrate what each of these parameters are, what type they are, the logic behind calling individual functions, and so on in a certain situation. All of this stuff is going to be available on GitHub. This goes into way more detail than I can reasonably go into in this video without overwhelming you. So I encourage you, go to my GitHub, pull down this code, and read through this. Understand every line as it's being called, because my goal here is to introduce you predominantly to the Windows API. This isn't so much a NIM video as a Windows API video. Try and understand the Windows API as it's being used to perform process injection in the examples I'm going to show you here. Okay? So all of the executable code is over here on the right-hand side. All of this is just comments. These don't execute. And let's go ahead and use this feature of Visual Studio Code and just minimize this function. This is the function where the actual magic happens. But to avoid overwhelming you, I think I'd like to go through the overarching structure of the program first. So the first code that's being actually executed here is this import Winim lean line right here. This is importing the Winim library. The Winim library contains Windows API, struct, and constant definitions for NIM. So essentially, what that means is that NIM doesn't know how to access the Windows API all by default. The NIM compiler does not understand the Windows API by default. That's what Winim is for. All of the functions, all of the constants, all of the structures need to be defined so that NIM knows how to call them properly. One way to do that is by importing the Winim library, which you can see right here. It is on GitHub at this location. And if you would like to install it, all you have to do is nimble install Winim. Nimble is a tool. It's basically the equivalent of pip, of Python's pip, but for NIM. And you can install this library, and once you've done this, you can import the library without issue, just as I've done right here. And this is going to be my recommended way for making your NIM programs understand the Windows API. There are pros and cons to doing it this way. You can actually do this without Winim, but you need to manually define all of the API functions, the structures, and the constants all on your own. And I've actually written another version of this program we're going to look at in just a little bit that doesn't use Winim, just to illustrate what the differences are. How does the code look different, and what are the consequences? Because there are some pros and cons to each. But again, the TLDR is going to be to just use Winim. This is just a function declaration, so this does not execute. It's just being declared. The next line that's going to execute is a conditional, just to see if we're in a Windows environment. That's all. Just make sure our program will execute gracefully in case it's not being executed in a Windows context. Now, there's then a nested conditional that checks to see if we're in a 32 or a 64-bit context. Now, you might say, Al, why are we accounting for 32-bit in our programs? Every single machine that currently exists in the year of our Lord, 2022, is 64-bit. There is simply no way that I will ever come across a 32-bit environment at any time in my penetration testing career. And I would say in response to that, you are partially right. The majority of machines on which this code is going to be executed are going to be 64-bit. However, two addendums to that. First of all, 32-bit machines are not nearly as rare as you think. Especially on the average corporate environment, you're going to have old legacy machines that are running that are 32-bit. You're just going to run into them all the time on just about every network you're ever on. It's very common to come across 32-bit machines. And second of all, and more poignantly, just because you're on a 64-bit machine, you're executing this on a machine that is 64-bit, does not mean that the process itself is going to be a 64-bit process. There are many Windows applications that execute in an emulated 32-bit environment rather than 64-bit, even if they're on a 64-bit machine. One of the most common and notorious of these is Office. Microsoft Office programs run in the 32-bit variety by default in most situations. And if you're running this program from Office, there's a really good chance it's going to execute in a 32-bit environment. So you want to account for that. Make sure you're accounting for the type of architecture you are likely to see. In this case, I've shown you how to account for both of them. Essentially, we're defining our shellcode differently depending on if we're in a 32 or a 64-bit environment. Now, this shellcode is generated using MSF Venom. No attempt has been made to encode or obfuscate this shellcode. So, obviously, there are risks of being caught by antivirus and EDR since this is being generated by MSF Venom. This is not an AV or EDR evasion video, so I've kept things as simple as possible. So we're looking at the raw shellcode being generated by MSF Venom. You would generate, if we look here at my, it's a little bit small. Let me see if I can make it bigger for you. Okay. So here we can see my WSL instance. I have my WSL Kali instance where I have MSF Venom installed, and we have generated this shellcode. This is the 64-bit variety. This is the command to execute this shellcode. As you can see, we are generating just message box shellcode. This actually doesn't do anything malicious. It just pops a message box. It's just used for proof of concept purposes, which this is. So that's all I'm using it for. You could easily replace this with a interpreter shell if you would like. And we're generating it in C# format. And the reason we're doing that is mostly because MSF Venom does not have a NIM format. The current version anyway. And the C# format, the shellcode is the same no matter what format you use. It's in a different format. I'm choosing to generate the C# format because I find that it's the most similar to NIM's format. It's easy enough to just copy out all of this, all of these bits and bytes right here, and also take note of the number of bytes right here, and come back over to our actual shellcode, paste it in right here. This right here is that shellcode that you just saw. You paste it in right here, and you make sure to put in the number of bytes that it is, because NIM is a statically typed compiled language, and arrays need to be defined at compile time. So when you're declaring an array in NIM, the NIM compiler needs to know how big it is, and it needs to know the data type that's going to be inside of it, so it knows how much memory to allocate. So that's what this is for. It's easy to just copy all of these bits and bytes right into a predefined NIM array and then just change this number. Easy. That's easy enough. Okay. So different shellcode is being generated and defined for the different architectures. And then we get down to when is main module. This is essentially the equivalent of if name equals main over in Python. It's basically just checking if this program is being executed and it isn't being imported like Winim is here. That's basically all it's doing. And if it is, it's going to call inject create thread, and pass our shellcode into it, our defined shellcode variable into it. This is where the actual magic happens. So that's all the main structure of the program is doing. All three of the programs we're going to look at today use this same structure. So hopefully this all makes sense. Now let's go ahead and minimize this, and let's take a look at the actual meat and potatoes here, okay? Again, please ignore the comments on the right. This is only for your edification. This doesn't actually have to be here for the program to execute. All of the executable code is right here on the right. So right off the bat, we're defining this function called inject create thread. To accept a parameter of a array, and we're going to call it shellcode. This I and T and this stuff, this is all just a NIM thing of how you pass a statically compiled array into a function like this. You need to tell the function how big the array is and what type it's going to be accepting, which I've done here. And we're going to be returning nothing. Void means we're not going to be returning any values with this function. And now we're just going to step through this function. All this function is doing is calling different functions in the Windows API. Remember from our slides what the overarching goal is. We're using CreateThread here, so we're not actually injecting into another process. We're going to be allocating some memory in our current process. We're going to be writing our shellcode into it. We're going to be making that shellcode executable, and then we're going to be starting a new thread in our current process to run our shellcode, to simply execute it. That's what we're doing at a high level. So let's step through one thing at a time. We're calling virtual alloc first. What virtual alloc does is allocate memory in the current process. I say that again, in the current process. If you would like to inject into another process, there is another function call for that, which we'll see that in a little bit. Virtual alloc is for the current process. Now, we're not going to go through every single parameter that's being passed to every single one of these functions, because some of them aren't all that interesting to us, and I'm trying to keep things as simple as possible for you. But I have included the comments on the right-hand side if you want more information. Essentially, the first thing we're going to do is we're going to pass null for the first parameter. This is telling where to start allocating memory, what address in memory do you want to start allocating. If we pass null to this, it's going to tell virtual alloc to choose some memory that's not being used. It's basically going to tell Windows to do the heavy lifting for us and choose a good place within our current virtual memory space to place our shellcode. We're going to tell it how much memory to allocate, which is essentially going to be the size. The size t is essentially a byte, and the number of bytes equal to the length of the shellcode. So we're basically allocating enough space for our shellcode. We're going to see this get reused quite a bit. And then we're gonna choose the memcommit allocation type. Don't worry about this. Memcommit is fine for our purposes. And then we're setting the permissions of page read write. We're going to set read and write permissions on this memory that we're writing. Okay? Now, the next thing we are going to execute, is write process memory. Now, as the name of this function indicates, we are going to write into the memory that we just allocated just a moment ago. Okay? Now, this first one, get current process, this could be a little confusing. This is another Windows API function call, but it's very simple. It doesn't take any parameters. And all this does is return a pseudo handle to the current process. Okay? Write process memory requires a handle to the process that we are going to be writing into. What is a handle, you might ask? A handle is very simply a identifier in the kernel to identify a specific resource. When we ask for a handle from the kernel, essentially we're saying, hey, Mr. Kernel, I am going to be interacting with this particular resource, and I would like you to assign an identifier to that resource so I can easily refer to it. Hopefully that makes sense. Get current process simply returns a pseudo handle to the current process that can be used like a regular handle. Base address is where to start writing. Which memory address would we like to start writing? In this case, virtual alloc has done us the heavy lifting of returning the first address of our newly allocated memory. So we're simply going to be passing in that address. Now we need a pointer to our shellcode in memory. What is a pointer? A pointer is simply a memory address. We're simply identifying, we're passing in the memory address of where our shellcode exists in memory, because this is what we want to copy. This is where we want to start copying from. We saw this again with we're seeing this again from virtual alloc. This is simply the length of our shellcode, how much memory to copy. We're going to start at the beginning of our shellcode and copy a number of bytes equal to the length of our shellcode. Okay? And that's all we're doing. We're taking shellcode from here and copying it here for this many bytes, for the number of bytes equal to the length of our shellcode. Hopefully that makes sense. Now, we're calling another Win32 function called virtual protect. we need to change the permissions on our memory that we've allocated up here to be executable so that we can actually execute the shellcode. Now, you might say, Al, why don't we just do this? Why don't we just do page execute read write right here? And you're right. Why don't we do that and just remove virtual protect? And the answer is because even though this isn't an AV EDR evasion video that we're making here, the answer is that I'm showing you a simple way in which these function calls can be manipulated to avoid and evade certain AV and EDR signatures. One common signature that is looked for is memory being allocated with page execute read write permissions, because that's having memory with permissions that open is not advised and is kind of rare. So this is considered suspicious by many forms of AV and EDR. So to avoid ever having memory pages with page execute read write permissions, before we write into it, we create it with read write permissions, and then we switch the permissions to execute read when we're done writing and ready to start executing. Okay? So just some considerations there for AV EDR evasion. Again, we're not going to go too deep into that, but I wanted to show at least one example. Now, the base address is, again, that address that's been returned, where our allocated memory starts. Where do we start changing the permissions of the memory? This is, again, how much memory to change of which we need to change the permissions. This is where we start. This is how much permissions to change. And this is what to change it to, which is page execute read. Okay? Very, very simple. And now we have shellcode in newly allocated memory, ready to execute because it has execute permissions. Now we're going to call CreateThread. CreateThread is used for creating a new thread within your current process. I'll say it again. Just like virtual alloc, this only works for your current process. If you would like to create a thread in another process, there is a different API function for that, and we're going to see that in just a little bit. Most of this function takes a lot of parameters, and you can actually play with these parameters to, again, do some more things that might evade AV EDR, but to keep things as simple as possible, I've set most of the parameters to null or 0, which basically tells Windows, hey, decide all of these things for me. Okay, I can't be bothered, Windows, decide for me. Okay? And the only notable thing we're passing in is the address, which represents the entry point for execution of this process, which is basically just the start of our shellcode. Remember, our shellcode was written starting at base ADDR, the base ADDR variable we declared way up here. So we're going to start executing right there. And that's it. We see that CreateThread also returns a handle to the newly created thread, so a new identifier in the kernel, if we do indeed need to refer to it. And as it turns out, we actually do. Down here, you see that I'm calling one more function here. Well, actually 2 more functions, but we'll get to that one here in a second. And the reason that is that our shellcode is executing. Once CreateThread finishes executing, a new thread is going to start, and that shellcode is going to start executing. However, we are at the end of this program. We're at the end of this function, and therefore, we're at the end of this program. So as a result, when the main thread finishes execution, this process is going to exit. And indeed, it will exit regardless of what this thread is doing. So it may very possibly exit before our shellcode gets a chance to execute at all. And if we have a interpreter shell or something like that, we're going to immediately lose it pretty much as soon as this process exits. So we need to call one more thing, wait for single object, which, as the name suggests, is going to and we're passing in the handle we just got from CreateThread. We're basically telling the main thread of this process, hey, pause your execution and wait for this thread to finish executing. Okay? So if we do this, it will keep the main thread. It will pause the main thread until the new thread we've just made here is finished. And we're also calling close handle. This is just good programming practice in a Windows environment. Once you're done interacting with a handle with the Windows kernel, it's a good idea to close that handle so you avoid what we call handle leaks. And that's it. That's all there is to it. That's a simple process self-injection example. So if we were going to compile this, let's go ahead and open up the terminal again. Come back over here. Now, this is a Windows PowerShell environment that we're in here, that I'm currently compiling this in. However, I'm going to show you a compilation command that will work on any platform on which Nim is installed. So we're going to start with nim c, and we're going to compile it we're going to do a release version. This removes debugging symbols, changes the name of the main thread, and a bunch of things. You definitely want to be compiling your malware for live use on a real target in release, in its release variety, because less signatures for AV and EDR to pick up on, a smaller executable, so on and so forth. We're going to add a few options, like we're going to optimize for size. We typically don't care how fast our malware executes. In most cases, we'd rather the Nim compiler try to generate it as an executable as small as possible for us. TAC-D, we're gonna specify the MingW compiler. That just says we want to produce a Windows executable. That's all we're telling it. We're going to specify a CPU architecture of AMD 64. Because we're going to be executing this particular program in a 64-bit environment. You could also do 32-bit if you wanted to. And this one is actually pretty important. We're going to be selecting a GUI app for today. There are two options you could have here. Console app is the default. The two options that are important to us right here are console and GUI. The console app is the default. However, a console app is an app that is designed to be executed in a command console. So if you don't have a command console when this is run, it's going to open a console window for you. And also, different DLLs and dynamically linked libraries, or DLLs, are going to be loaded into the process to begin with. So certain shellcode may not execute properly in a console window. Like, for example, our message box shellcode. Recall that we are executing message box shellcode. This message box functionality only exists I think it exists in GDI32.dll, which doesn't get loaded into console apps by default. So you need to load it. If you want it loaded, you're going to have to generate it as a GUI app. And GUI apps are generally better for us because GUI apps will not open a console window upon execution. However, AV and EDR may scrutinize GUI apps a little bit more than console apps. So there's a consideration there. So pros and cons to both. Just things to keep in mind, okay? We're going to specify an out directory, a directory in which to write our resultant compiled code. And I'm just going to, I have a directory called compiled inside of this process injection directory for our compiled binaries. And then we're just going to specify CreateThread.nim. Okay, let's go ahead and compile. All right, and we get the success message. We don't get any errors. So let's go into our dev environment. And you'll see I already have everything open in File Explorer. We'll open up the compiled directory and we see the exe we just compiled. Let's go ahead and execute it, and we see a message box saying hello from MSF. Great, fantastic. And we hit OK, and our process terminates. No problems. We've successfully injected into our own process. Spectacular. Spectacular. Let's proceed a little bit, get a little bit more advanced. Now, I recall that I told you that it is possible to do this same thing without Winim, without the Winim library. Okay, this is using the Winim library. I'm going to show you what it looks like without the Winim library. So let's open up this CreateThread no Winim program I got here. Okay, close that. And you'll see this is a functionally equivalent program to what we just executed. You'll see that it has a very similar structure. The actual executable code looks exactly the same, right? But it's preceded by all of this junk. Look at all of this mess. We have to we have to basically, one of the things we have to do is we have to declare a macro to define a new pragma that we're going to use for our function calls. You come down here, you see all of the functions being declared. This is called a function prototype. It's basically telling the Nim compiler, hey, this function called virtual protect is actually located in kernel32.dll and has all of these different calling conventions and so on and so forth. It accepts these parameters and has this return type. It's basically telling the Nim compiler everything it needs to know about these various functions so that it can call them in the program. Okay? And notice that not only do you need to declare these functions, but that, like, for example, virtual protect, it probably doesn't know what an LP void data type is, or what size T means, or what a D word is. So you have to come up here and you have to declare all these types. Like, say, hey, a D word is a 32-bit integer. And an LPD word is a pointer to a D word. So an LPD word is actually a memory address. And a handle is just an integer. And so on and so forth. And you have to do this for all of the types that you're using down here. Okay? And this obviously can be a pain in the ass. Like, this is a huge pain. But you see that when we actually get to this is all identical code to what you saw before. All of this is identical. It all executes the same way. Same shellcode being executed here. And if we come over here to our terminal, we can execute the same thing. We can compile the create thread no winim. We get the success message. We've successfully compiled. We go back into Windows. Let's reload the directory. And we now see create thread no winim. We execute it. And we get a message box popped the same as before. Now, what are the pros to doing it without Winim? You get a slightly smaller binary. If you see over here on the right-hand side, you can see the size. Hopefully that's big enough for you. Basically, it said the create thread with Winim is 126 kilobytes, and the variety without Winim is 124 kilobytes. So you've saved yourself all of 2 kilobytes of space by not using Winim, which is really negligible. In like 99.9% of cases, that is a negligible amount of bytes to save. So in general, you just use Winim. Just use Winim. I'd also like to highlight, this is a strength of Nim for attacker tradecraft. Look how small these binaries are. If you compiled a program just like this one, using create thread to execute shellcode in like Go or Rust, the binary is easy going to be over a megabyte. It's going to be a thick boy. Like, we're talking probably 10 times the size of this binary. And that's may potentially not be a problem to you, depending on how you're using it. But in general, having smaller binaries is preferred, especially if those binaries are being downloaded or transferred over a network or something like that. The bigger a binary is, the more unwieldy it is to use, and the more chance it has to get detected. So this is a strength of Nim, is just the size of the binary. And you do get a slightly smaller binary without using Winim, but in my opinion, that's a negligible amount of size, but something to keep in mind. Alrighty? So let's look at our last example for today. We're going to look at one more example, and that example is going to be using CreateRemoteThread this time. Okay? So let's open this up. Don't save, sure. And let's take a look at CreateRemoteThread. So right off the bat, you see again, the structure of the program is the same. We're declaring the shellcode the same way. We're using the same shellcode here, and we're just calling inject CreateRemoteThread. The only thing that's changed has been the actual functional has been this stuff up here. Okay? Let's go ahead and expand everything. I had a couple of them minimized for some reason. This is the actual function in which the magic happens. Inject CreateRemoteThread. But you see we have these other functions up here. We're going to explain what this is. But it's easier if we just minimize these for right now. And we start by just looking at inject CreateRemoteThread. We declare it the same way. We're just passing in our shellcode as a statically defined array. And we're not going to be returning anything. Now, the very first line is a little bit different, though. And let me explain what this is doing. Essentially, both of these other functions that exist in this program exist just for this line. And all that's happening here is it's finding a process called explorer.exe. It'd be easy enough to change the process here or make it defined on the command line. But for simplicity's sake, I've selected a good process to inject into, which is in explorer.exe. It'll be good at illustrating what I'd like to illustrate today. And then we're going to execute the getProcessByName function. This is not a Win32 function. It's declared right here. GetProcessByName is essentially going to use Win32 functions to iterate through all of the Windows processes and look for one that matches the name that it's looking for, essentially. Okay? In this case, the name is going to be explorer.exe. It's going to iterate through all the processes to look for one called explorer.exe. When it finds that, it's going to return the process ID, the PID, the process ID for that process. It's also using, this is kind of a NIM-ism, this two-string PPID business. This is kind of just a NIM-ism right here. The Win32 functions here are going to return an array of characters rather than a string, and we just need to convert them to a NIM string with a null byte at the end of them. So we have a separate function here to do that for us. This is just a helper function. You can think of it. But basically, all these functions are doing is finding a process that matches this name, and it's getting the process ID. Easy peasy lemon squeezy. Okay? So with that process ID, we go into our first call. We're going to open process. Open process is going to return a handle to a given process with the given permissions that we need on that process. Essentially, what we're going to do is we're going to provide it the PID we just gave, okay? And we're going to ask for all access to that process, all right? And once that's granted to us by the kernel, we're going to ask it to assign a handle to that new process that we've accessed. And we're going to be using this handle throughout the rest of this program. Now we're calling virtualalloc EX. EX. Recall that the previous function we used was virtualalloc, and this is virtualalloc EX. I think EX stands for extended. Essentially, it's exactly the same as virtualalloc, except it works in processes that are not the current process. And it takes all the same parameters that we saw over in CreateThread. It takes all of the same parameters, except for one additional parameter, which is the handle to the process in which we're trying to inject. Okay? So we're calling it the same way as we called virtualalloc before, except we now have an additional parameter, which is just the handle that we got from open process. Okay? Now we're calling write process memory. Same thing as before. This is the same function as with CreateThread. It's just we're now passing it the handle for the other process rather than a pseudo handle for the current process. Okay? But other than that, identical. We've seen this before. We come down, virtual protect EX. Again, previously this was just virtual protect. Virtual protect is used to modify pages of memory within the current process. Virtual protect EX is used to modify pages of memory in other processes. But it's called, again, the same way with the same parameters with the addition of that handle that we got with open process. Okay? So you're seeing a pattern here. Hopefully the Win32 API is starting to make sense at this point. And because, once again, we're going to do it again with CreateRemoteThread. And as the name indicates, this is used for creating a thread not in our current process, but in the process in which we are trying to inject. All the same parameters are being passed as with CreateThread. We're just also including now a handle to the process. Okay? And you'll also notice that we're not calling wait for single object down here. We are not calling wait for single object because we're injecting our shellcode into an entirely separate process. If this process terminates, it doesn't matter. We've already created, our shellcode is running in a different process entirely. It doesn't matter if this program finishes execution. We don't need to call wait for single object, which is spectacular because that's less signatures for AV and EDR. AV and EDR often detect on a wait for single object after CreateThread, I find. But this avoids that, which is real, real nice. So there is a simple create remote thread example. Now, we are going to get some weird behavior. This code will run, and I'm going to demonstrate that in just a moment. We're going to compile this code. It will compile, and it will execute. But we're going to get some weird behavior, which may or may not be desirable for you in your specific use case. So I'm going to go over it. So let's bring back our terminal, and we're going to execute. We're going to compile CreateRemoteThread.nim this time. And it compiles. We get the success message. Excellent. We'll bring this back over here. We'll open up our test environment, and we'll open up the compiled directory. And now we see create remote thread. And if we double click on it, we see that we get a message box the same as before. However, if we click this OK, SpaghettiOs, what just happened just there? Why did our screen go black for a second? Why did our windows close? Our File Explorer windows close? That didn't happen before. And the answer is because Explorer.exe exited. Explorer.exe is the process that's creating this desktop environment that you're seeing, that you see on Windows. That's what Explorer.exe is doing. If Explorer.exe exits, it will get restarted immediately because Windows is designed to just restart Explorer.exe in case it ever crashes. But obviously, it closes all the windows, the File Explorer windows. We don't like that. That's bad. The user might be set off by that. That's not ideal. We don't want to be bothering the user by terminating Explorer.exe or any process in which we happen to be injecting. So what has gone wrong here? Let's look back again at our shellcode. Okay, recall it's executing in a 64-bit context, so we'll focus on this shellcode for right now. Okay, this shellcode was generated by MSF Venom, and MSF Venom automatically, by default, sets all of its shellcode to have an exit function of exit process, I believe. I think it's called exit process, which means that once the shellcode finishes executing, by default, once MSF Venom shellcode finishes executing, it will exit the current process. That's not desirable. So we can change that default behavior by adding the option exit func equals thread. This tells MSF Venom, hey, when you generate this shellcode, instead of exiting the process, I just want to exit the thread once it's done executing. That way Explorer.exe will not exit and need to be restarted. So we can hit this. It's going to take a little bit to generate because WSL does not have the best performance in the whole universe. So I've already actually generated it for us over here with an explanatory comment. So I'll just copy it right here. We'll go into Visual Studio here. We'll go ahead and we're going to comment out. This is how you do block comments in Nim. You do like this, these angle brackets and the pound symbol. So we're going to comment that out. And now we're going to paste in this other iteration of the shellcode. You see this shellcode is a slightly different size. It's 323 bytes instead of 295. And we see that MSF Venom has now finished, and we see that it's 323 bytes. It's identical shellcode. I was just demonstrating how to generate it. But we see the shellcode is a little bit different. And now if we save this, let's make sure to save this. And let's go back in here. Let's recompile this. Recompile a new version of this. Okay, cool. And now we go over here. I have a shortcut here that we can open up. We can open up the compiled directory. We can execute create remote thread. We see a message box as always. And then if we hit OK, we see Explorer.exe does not terminate on us. And everything continues as you'd expect. Okay, so that is all there is to it, my friends. Those are some simple process injection techniques in Nim for the enhancement of your brain wrinkles. Okay? So that's it for today, my friends. I hope you enjoyed this quick foray into the deep magics of the Windows API and process injection. As I said earlier in the video, the code that we explored today has been pushed to my GitHub, and the link to the repo is in the description below. I've added tons of comments to the code and gone into much more minute detail to explain it there than was really appropriate for this video. So feel free to pull it down, read through it, play with it on your own machine, and do whatever you want with it, really, as long as it's legal. That's where the real learning happens, my friends, when you get off of YouTube and you actually start tinkering with stuff in your own little lab. Let me know what you think of this new series. Any feedback is appreciated because I want to make a lot more of these. I want to explore more process injection techniques, AV EDR evasion, custom C2 development, ransomware, lateral movement, exfiltration. Basically, if malware does it, I want to explore it and deobfuscate it right here. Your thoughts and suggestions are invaluable to me, so I can bring you what you want to see. If you did enjoy this video, if you added a few more wrinkles to your brain, it really helps me out if you go ahead and drop me a like. And if you want to see more of my content, it helps me more than you can possibly know to go ahead and subscribe. If you have any questions, comments, threats, bribes, feel free to reach out to me on Discord or drop them in the comments below. I am also live on Twitch 3 times a week teaching all of these eldritch magics. So check me out there as well. Go to bed tonight knowing a little bit more than you did yesterday. I'll see you guys again when the stars are right. Cthulhu fought and cultists. Bye for now.